So first announcement is that today it's a holiday in Germany. It's Easter holiday, so there's no joint class with the German students this afternoon. Of course, you can still contact them to discuss your progress and your project, but there won't be an official class, and then you can wish them happy Easter. Ask them if they got any Easter eggs.
I tried to look for Easter eggs yesterday. I was not lucky. I didn't find any chocolate eggs in Taiwan.
Oh, okay. But yeah, like where, in Dan Park or what?
Around Dan area, yeah.
Oh, okay.
It's fine.
It's just not a thing here, right?
Yeah, it's really not a thing.
So last class, on Monday, we discussed feature trackers, right? Feature points. And in particular, we looked at the ORP feature points, which are by far the most popular ones nowadays. Mainly because the previous versions of the feature points that were proposed by researchers, they were in common with patents. So both SIFT and SURF features were there were patents on them. So OpenCV used the open version of it. Nowadays the patents have run out, but people are so used to the ORP features that they just keep using those. Apart from that, it probably doesn't make a huge difference about what kind of feature detector you use. It's more an issue with the particular domain that you have and the way that you are thinking and tracking those feature points. Now, they all look for points that are unique within their local environment, that are invariant to changes in rotation, that are invariant to rotation and invariant to changes in scale. Because if you have a local robot and it moves around, then things are going to come closer, so it's going to zoom in. Now, our next step in using these feature points is to try and develop algorithms for allowing the robot to navigate through the world. And the idea is fairly intuitive, right? If I walk, I know that I'm walking because the world is moving in accordingly, right? In what I would expect from my motion. And this effect is actually quite strong in people. Let me see if have I shown you that video already about the person and the walls moving in the room?
No.
No? Okay, this one is a very cool video, so I want to share it. I guess last time I searched for the same thing.
你需要吃益生菌，可以帮助消化，但你吃了益生菌可以健康多吗？决胜结束。
So this is obviously some dated research, but the basic findings are very interesting. Done by a guy called David Lee, who was also he was a psychologist, but he was also interested in the feedback loop that we humans use in our balancing as it comes from the eyes. As well. How much do we use our eyes when we're balancing? Right? Now, the basic effect is quite easy to demonstrate. If I get you all to stand up quickly, actually, just stand up. Okay, then try and balance on one leg. Okay, now close your eyes. And then most people, oh, you're like the yoga champ. Or dancer, okay.
There already.
Yes, okay. For most people, once you close your eyes, it's actually quite a bit more difficult, right? You can definitely tell that it's harder to balance once you close your eyes.
It's interesting. I thought the equilibrium was in the ears.
The equilibrium is in the ears, right? You can certainly demonstrate that. There's actually a funny video of me because how do you demonstrate how important the inner ear is for balancing? No? Okay, what you have to do is pick any object. Traditionally, it's a stick or something. And I don't want to do it here because we don't have enough room. Right? But you hold the stick, you ask people to run around the stick quickly, right? And you guys probably, if you need to do like the dancing, the pirouettes, you probably have to practice this seriously, right? And what happened is, I told this to my students, right? I said, hey, you can see the inner ear, how important it is for balancing by running around the stick. And then they're like, okay, I run around the stick. Oh, nothing happens, right? And then I said, no, you have to do it like this. You actually have to run. So then I run around, and obviously I got up, and then you ask people to run in a straight line, right? And I only took like 3 steps, and then I fell down already.
So there is a video of this.
Yes. But it's just because my students didn't do it properly. Like if you go too slowly, then of course you're in the ear. So yes, we balance in our inner ear, but that's a majority of the balance, I think. But we also use our eyes. And another effect that you're probably also familiar with is that if you go to a river and you stand at the bank of the river and you see the water moving by, right? If you watch the water flow by, then if it's from the side, right? So you stand like this, the river is like that, and the water keeps rushing by. If you do this for a couple of minutes, then all of a sudden you're convinced you're the one moving, right? You're like convinced I'm moving upstream instead of the water running downstream. Right? So the eyes play an important part, and I think this psychologist did some very interesting studies. For what?
Oh man, just under cheap ways to get high, looking at the river.
Okay, I didn't want to bring it into that.
It's safer than drugs.
Yeah. And I actually don't know, but I think Taiwan is pretty tough on drugs.
Oh yeah,
They are.
So
They are.
just a word of warning. Hey, dude. Yeah, I know. If you're from California, I have some students from California coming, and that's a good point. I better tell them.
Better safe.
Better than safe than being in jail.
Yeah. So anyway, let's watch the rest of the video. But boy, yeah, I really hit hard when the stick froze.
The soil is small. The draft is easily maintained. But if visual information is important, then it should be possible to upset a subject's balance in an experimental room by moving the room gently forwards or backwards. Infants learning from sound are less stable than the adult, and find ways to put off balance.
So I'm not even sure whether you could do that kind of research still nowadays with human subjects. But here they have a little baby and they're just learning to walk. And then the researchers build a room that moves the walls, right? So you can see the walls move, and then the kid falls down.
Oh. Okay, that's.
See, now the room moves. The kid is like, oh, hey!
Oh.
So for a human, for an adult, it's not a problem. See, now the room moves a little bit, but the guy's not. So now they give him a more difficult balancing problem. So if it's a more difficult balancing problem, then you still use your eyes. And sure it does. So I thought that was a pretty neat experiment. It does show that even for adults, visual information is still important for balancing. And it's basically using this, we want to use the same idea for our robots. We do have IMU sensors on our robot, so we can actually track the movement of the robot, but those are inherently noisy. In particular, the linear, there's two types of IMU sensors. One, we can use gyroscopes. Gyroscopes give you a reading of the angular velocity, so they tell you how fast you rotate. Now, that is the sensor is quite accurate, but the problem is noise in that case will accumulate. So if you rotate between plus and minus 10 degrees for several times, and then you stop at 0 degrees, then if you start at 0 degrees, all of a sudden you're off by 3 degrees or 4 degrees, because all the errors are accumulating. And that, of course, then already would make your robot fall over if you have an error of 3 degrees. But for short periods of time, the gyroscopes work very well. The other sensors that we have available are accelerometers. Accelerometers allow us to measure the linear acceleration of the robot. And I talked about this previously, but if you want to get the position of something, right, then your acceleration would be the second derivative that you use in order to measure what you're actually trying to measure. Right? So there, any noise will be greatly amplified. So it's very difficult to actually get the position from the linear acceleration. There's quite a bit of noise involved. The other, however, the clever thing you can do with the accelerometers is that the 3-axis accelerometer reacts to acceleration, and even if I'm standing still, then gravity will still act on me, right? So I can still measure acceleration. Even if the robot itself is not moving, there will always be some acceleration measured due to gravity. And I can use the accelerometer to basically measure the direction of gravity. So in that case, I'm not actually considering, I'm not trying to say, oh, I accelerate with 1 meter per second square, and now I did that for this long, and now my acceleration is minus 1 meter per second square. How far did I walk? That is not robust enough. But it's actually a pretty good measurement for what angles do I currently have, which allows us to basically reset our gyroscope angle. So both of those combine. If you combine your accelerometer with the gyroscope, then that's usually called the inertial measurement unit, IMU. And there's pretty clever algorithms for, I used the metric algorithm last time, for actually then calculating your angles. So, but position is really difficult. But you can also see that if I have a calibrated camera and I can measure distances to points, at least from my local point of view of the robot, then if I can track those two corners of the tiles, and I can see them move, and I can now measure my distance to those two places. Depending on if you have your information or not. If you don't have your information, you actually need 3 points. Otherwise, 2 points will be sufficient. Then you can use that to actually localize your robot within the field of view that you had before. And then you do that continuously. That means you can start building up a map of the environment. So we can interleave the localization step with the mapping stage, and then that allows us to build a map of the environment. And that would be the perfect solution for the obstacle run. You can get by with just running a local obstacle avoidance algorithm. That also will get the job done for that particular environment. But if you want more, if you have more complex environments, like a maze kind of factory floor or something like that, then you would need to do a better job in your mapping implementation. The other thing that I implemented was a system that ran on the Android phone that basically did that, exactly what we're doing today, the Lucas Canade feature tracker with a couple of ideas added in. And the reason for that is for our humanoid scooter project, where the humanoid robot is supposed to drive the Gogoro scooter. In that case, it actually turns out that our control is quite good, in the sense that if we give it the correct velocity and the correct lean angle, it actually figures out how to steer correctly. So that's cool. But and our lean angle we can get from the IMU. We can get using gyroscopes and accelerometers.
Linear angle of what?
Pardon?
Linear angle of the. You mean the angle of the.
No. I mean the scooter, whether it's leaning to the left or to the right. The lean angle of the scooter is very important. Based on that and the velocity, we calculate our steering angle. Then we have inverse kinematic step, where we actually, and that one was actually quite a bit harder than the current research literature would have you believe. It was quite an interesting experience, simply because I would say that the reason why we do things like that is, and not, like, if you were to build a self-driving scooter, right? That's one thing, then you need to worry about the balance and things like that. But if you build that, then clearly the optimal solution, or the good solution, would be to have two motors that control the two different inputs to the system that you have to control, right? One, your steering angle, so you build one motor that can turn the steering column, and two, the throttle, right? So you have one motor, and the Yamaha built a self-driving motorcycle, and that's what they built. They have one motor for the steering, one motor for the throttle. And then, of course, everything is nicely decoupled. You can control one without impacting the other one. But that's not what humans do. And we want to see if we can do the same kind of things as humans do with our humanoid robot. And it actually was surprising to me too, because what we realized is one of the problems that you have to solve is, if you have a controller, the controller will give you a steering angle and a throttle setting, right? In order to drive the scooter. So there's two values that we need to generate. If they're decoupled, you just send one to the steering column and one to the throttle. The throttle is the gas.
Ah, okay. Okay.
How much speed you give.
Right.
Yeah. Now, in our case, they're coupled, right? Because the robot hands are going to move the steering wheel, but they also have to move the throttle to give it the correct angle. So there's two angles that we need. And what is interesting is that particular problem, we now know we need the steering angle, right? And we need the throttle setting. So now our robot, which doesn't just have motors and angles, right? We need to move the arms. In order to move the arms, it's not just one motor that needs to be in the correct position, right? It's all the motors in the wrist, the elbow, the shoulders, the torso of the robot. And both of them have to be in the correct position. And that particular problem is called the inverse kinematics problem. You're trying to map from the world coordinates of your end effector to the joint coordinates in your motors. And that's a problem that has been studied in robotics for 60 years. Right? Since the very beginning of robotics, this problem has been studied. And it's non-trivial to solve, not because it's similar to the mathematical problems, right? It's not really a math problem, because in math, you would think it's a difficult problem. That means that there's actually very few solutions to the problem, right? Our problem with inverse kinematics is that if you have more than two links in your system, then there's actually too many solutions. There's like infinitely many solutions. And somehow your algorithm has to pick one that actually is reasonable. And so that's the inverse kinematics problem, and the way that is usually solved is using a gradient descent algorithm on the error. And you define the error as the error in the position. So you want the gripper to be here, but your gripper right now is here. So you make small movements to move it closer to the target location. That's the inverse kinematic algorithm. And very well understood, works like a charm on hundreds of thousands of robots in industry every second. It's one of the fundamental problems. And I'd worked with inverse kinematics before as well for our humanoid robots. For example, for basketball, we need to bring the arms at the right position so we can pick up the ball and things like that. But the scooter, driving the scooter, it was the first time that I actually realized that inverse kinematics is much more subtle than we thought about, because the error predicate, the error function, although if you want to do it with a neural network, you can do the same thing. You just call it a loss function and you run the gradient descent on there. But what was interesting with Scooter is that the error was only based on the difference in the position between the current location of the end effector and the target location, right? But when we drive the scooter, if we have a little bit of error in the steering, it's actually not a big problem, right? We can compensate for that usually. But if our throttle goes from here to there, it's extremely sensitive throttle on the e-scooter. The scooter will go from 10 to 35 kilometers per hour in like 1 or 2 degrees. So that means that our inverse kinematics formulation is actually incorrect, because we need to have a multi-valued optimization function. We need to say we must have the angle much more accurate than the actual steering angle that we get as an output. So, and that was the first time that actually happened. Like if you're a CNC machine robot, right, then any error, plus or minus xy, plus or minus xy, is usually the same. There's no difference in the errors that you may generate. For the scooter, there's a huge difference. The throttle is really, really sensitive. So when we just ran the standard inverse kinematics algorithm, our velocity was all over the place, which is not safe, of course. And it also made it hard to apply the correct function for the control, because the control needed the current velocity of the scooter as input. And it was also very sensitive to the current velocity. So we actually run optical flow now on our scooter in order to measure the current velocity. We tried a couple of things. GPS, of course, would work if we're outdoors and we have good GPS reception, but it's not really accurate enough.
There should be sense.
Huh? It's, well, we need to have the velocity every time when we balance the scooter. We need it for more than the 10 meter, this locked 5 meters that you get with GPS. IMUs were too noisy because of the road. It's not a flat surface that we drive on. So we actually use optical flow in order to measure our velocity. Now in that case, you don't talk about a visual slam algorithm, but that kind of algorithm would be called a visual odometry algorithm, because we're mainly interested in the motion that we're doing, our current velocity, our current turn rate, more so than building a map of the environment. That's kind of a secondary concern. But getting real-time information about the velocity was very important. So that's what we were doing with the camera. I implemented it using vision alone, but we also have one of the Intel RealSense cameras, so we can actually get 3D information. Any kind of navigation task, if you get 3D information, then it's much easier. So, and of course it's safer, so we now use the RealSense, but we could also just use a standard webcam. And I think it would work. It wouldn't work so well with if it's a scene here, driving on the NTNU campus is problematic if you have people moving around, because then of course you get the same effect as looking at the river. All of a sudden the robot thinks it's moving, but it's not. It's just all the people that are walking in front of it.
You mentioned the example of the museum, right? When they launched the tour guide, young people.
That was also a fun story, yes. So they had a problem because all the people were all of a sudden in front of the robot, and somebody clever came up with the idea of looking at the ceiling. That wouldn't help us, right?
No. Kill Terminator.
Yeah. Of course, it would be kind of fun to have scooter, and then when the scooter drives, it's just looking all over the place, right? Never in front of it. Then to see what the reaction of the people would be, because of course the scanner could be in the front, actually we could make the head move anywhere we want, right? But it would definitely
not really.
would scare a lot of people if the scooter, if the robot doesn't look like it's paying attention. So there's kind of a HRI component to that. I also think it is wrong by Tesla, Elon Musk, basically has decreed that the autonomous cars at Tesla will never use any LiDAR scanners or radar, microwave.
What do they do right now?
They use cameras only, but that is a much more insecure technology. And if I do it, because we do research on humanoid robots and we run it not out in the open road, we don't sell millions of units to people to just drive on the highway or in the city anywhere they want. Then of course we can do that as a good research goal. But if you are supposed to build a safe product, then I think adding the best sensors that we have available is a must. It's not really ethical to not use them just because there won't be much difference in the cost of the car, right? It would be a minuscule difference in the cost of the car. You're just better testing it on the general public.
I wanted to work on my master thesis on autonomous vehicle driving, but my supervisor said, I gave him some ideas, I was reading some papers, etc. And he said, I'm convinced that we can build the perfect autonomous driving car just by using two cameras, because humans just have two eyes. So one camera, a stereo camera, needs to be enough. If you want to work on that, that's fine. Otherwise, change something. And I change topic because I can't. But there are many people apparently that believe the camera, driving car, only the camera. But I mean,
well, humans can do it with two eyes, but there's a huge difference. For one thing, the two cameras while driving the car is not useful at all. Like you could do the same thing with a single camera. I'm sure there's one-eyed drivers that can drive the car just fine. And the reason for that is because your stereo vision effect, right, is what you use if you need to thread a needle, like around this distance, like 1 or 2 meters in front of you, right? Anything that's further away, like that door, I have no idea about the position of that door, the distance to the door, or anything, right? Because the parallax shift in your eyes is actually too small for your brain to make any reasonable deductions about the distance to the door. I know how far the door is away because, and I would estimate, 7 meters? We should have one of the little laser measurements. The reason why I know that is because I know how big doors are, and I know how big they are, and I know distances that I've run before. So it's actually a lot of work model that people use during driving. the stereo camera, I think for a researcher that's a good goal to say, oh, we want to do it only with stereo vision, right? That makes it a nice research project because there's of course already a lot of companies. There's a lot of companies working on self-driving cars already, and two of my students, one was working for Waymo, the other one was working for Apple. But Apple now shut down their car project. But I think that's a good research topic to say, oh, how much, like how safe can we make it? But that's in order to get your stereo vision as safe as possible, and then you will combine it with a laser scanner in order to make it more a safer system, I think, if you actually want to sell it to the public or have it drive on public roads without a safety driver. I think that's the ethical thing to do. But there, of course, there's no problem with doing research on stereo vision. But for autonomous driving, I think lots of people are working on that already. So that's why we do the scooter and the driving test. License test to see if you can pass the license test. But stereo vision is actually, for humans, I think most of the information that we use navigating through our world is actually not based on stereo vision. It's actually based on anything past 2 meters. The parallax shift is quite small, so your brain will be able to measure distances exactly. But it's kind of interesting to ask people to measure distances because most of them are really bad. Like one time, my wife and me, we like to go hiking, right? So there was this lake. I don't know. That is quite famous, I think.
Some lake. No.
I have no idea. I only go there with my wife. I never know where I am at. But it has a special. I think. Yeah, this one. This kind of lake.
Oh wow. That's beautiful. Oh wow.
I was there. Yeah.
Wow.
Jiangming. You know this one?
Never been. No.
No.
Beautiful.
I think it's a 3-day hike to go there. 2-day hike or something.
Oh, I'm gonna take a picture.
Yeah. So it's very nice. But the folklore is that when you get to that lake, you have to run around. This is actually still quite a bit away, but you have to go down into the valley there, and then you have to run around the lake for good luck, right? So that's the thing. So we get to the bottom of the lake, and there's a big group of people, right? Like 20 or so, 15 people. And then they say, oh, we're so tired because we were walking, hiking there. And then, oh, we're so tired. Oh, I wonder how far it is because now we have to run around the lake, all right? And then they say, oh, how far is it? And then people are like, oh, 700 meters, 800 meters, 900 meters, right? 950 meters, right? Around, because you have to
circle it. Yeah.
You have to circle around this thing. It's not the distance here, right? And I stand there and I say 350 meters, and they're all like, no, much too short. Like I was way below all the other measurements, right? Then we use the Garmin watch, run around 375 meters. But you know why?
What did you do?
This was very funny. Anyway, they were all very surprised that I got the number so close.
It's not like 50 or 100 meters difference. It was like half.
Yeah, that's because when I was young, I was doing this. Like that's me.
Oh, okay.
At the World Championship in thing. So I used to do speed skating, right? So that means that basically my entire life I've done thousands and thousands of laps around 400-meter racetrack, right?
Okay.
So I knew exactly how big that is. I was like bored for that lake. There's nobody in the world that could have guessed that any better, unless it was another track and field athlete or another skater, right? Because I got there and I knew that this is just a little bit shorter than race lap than when we had to do training. So that was funny.
That's a nice
but
use of your.
Yeah. 12 years of training for this one moment in time. Finally pays off. Right? But it's humans are very bad at measuring distances in general. And the thing is, we expect these robots to be able to do that from the image, as if people are like super accurate. And some people are if they have a good enough world model and enough experience, right? But for the average person, it's a difficult task. It's a difficult problem. Anyway, yeah. So this is, I didn't know, but I was there at Xiaoming Lake. I remember the lake and how far around it is. Oh, yeah, here they do like the hike. They did it in 4 days. Maybe go a little bit further. So let's have a look at our test video. It's quite easy for people to see how the person moves, right? Like which way are we moving now at this point? Backwards, right? Yeah. And
Looking down.
Looking straight.
looking straight, yeah. Looking down is because the I have to scroll it. No, but if you look at it again.
So it moves forward a bit.
Yeah.
For a while, and then stops.
Mm-hmm.
And then moves backward.
Right.
Left, right.
Left, right. Yeah.
Left,
so
right,
it's quite easy to do that for. So we want to be able to do the same thing with the robot. So when we move forward, our points, if you look at the trajectory of the points, you can see depending on their height, they will either move up into the outside of the image or down out towards the outside of the image. When we move backwards, the points move towards the center of the image, where this is not really the center of the image, it's sort of the optical axis of your camera, the direction that your camera is pointing in. If we rotate left, then all the points move to the right. If we rotate right, all the points move to the left. Now in this case, the points will move due to the motion of the robot or the camera. Right? There was nothing in that image that actually so you can watch it yourself. Like that was basically a static scene, right? There's not cars moving or pedestrians walking or something like that. That's what we would have had to contend with. But I cannot detect the motion of all the pixels. So we need to have some trackable points, static points where the movement is due to the robot movement. In this particular video, these points here and these points, they would be problematic because as we go through the video, the reflections actually move with the robot. The highlights actually move because they are the reflection of the lights on the ground. They're not actually points that we can track. So even in scenes where you may expect that there would be no problem, the kind of reflections like this would be very nice points to track, right? It'd be very easy to track using any kind of feature detector, but they would actually throw off your result. So we need static points. We want points that remain in the scene for the next frame at least, or ideally for the next couple of frames. That also makes sense, right? If I'm moving so fast that the points are disappearing by the second frame, then of course I won't be able to track their motion. They need to be in consecutive frames, a minimum of 2, but more is better. They need to be unique in the global image. That will be the perfect case. If we cannot get points that are unique in the global image, then at least unique within their local neighborhood. Like here, the corner points of the tiles are very nice feature points to track. Right? They won't be perfect, but they're not really globally unique because each intersection looks the same. They're all like black crosses on a white background.
This is for several avoidance, right?
This is for any kind of motion estimation, which could be visual odometry and then build up on visual slant. Okay. But as long as I can keep tracking them, keeping identifying them, it's okay, right? As long as they're locally unique.
When I run for, it just gives me features in general. Check features of the image.
Correct. Yes.
So how?
And org is looking for local features, right?
So you want
so it doesn't take the global part of the features into consideration. Org will just give you the points that it considers are good features.
Yeah.
But you can look at the descriptor and, for example, measure how close the descriptors are in order to be able to see how much different those points are. Or you can do a post-processing step, looking at the actual feature points that you detected, and then prefer the ones that are unique with respect to all the other feature points. Because if I look at that, or if I'm in this scene here, right, and I track um, the intersection of the tiles, I can do that as long as I move slowly enough. The tile intersections are going to move a little bit, right?
Yeah.
But I still know this is tile intersection 1, this is intersection 2. But of course, if I run much faster, then that association between the previous feature point and the next feature point, that may got lost.
So we want also to memorize the number of intersections that we have passed. Or this is just an example?
This is just an example. If I were to use, if I look at my orb feature detector and I use features on the blue chair, then those would be better points, right? Because there's no other blue chair here. Like, even if I'm spun around, I don't know which way I'm looking, right? If I look for the blue square chair, then I'm aligned again.
Okay.
But it's true that the orb feature detector doesn't make any distinction between, as long as it gives you all the locally unique or distinguished feature points. So today also we want to look at some important characteristics of feature detection that are quite important if you're trying to apply to robot motion and navigation, those kind of challenges. They need to be robust with respect to changes in the viewing angle, because we'll look at them from different points of view. Robust to changes in illumination and brightness, robust to changes in rotation, and robust to changes in scale. Because as we move, things will come closer to the. Now, one problem that we have with any kind of visual navigation is as I'm tracking the points, that only allows me to estimate the movement in pixels per second. It doesn't really tell me how many kilometers per hour my scooter is going. So that's called the scale problem. So it's quite easy to get the direction that the robot is moving in, but you need additional information to work out what the actual scale is of the movement. Single camera can provide information about a vector from the camera to the point, but we don't actually get any distance information. So then you can use additional methods in order to find the depth of your points. One is stereo vision, 2 cameras. That's usually quite close into the robot, like 1 or 2 meters. Also the same for humans, where we use stereo vision. Range finders. You can do things like, if you have additional knowledge, and that's what humans do most of the time, we know how big things are. And because of that, we can estimate distances to things, or the position of objects. So if I know that the door is on the ground, then if my camera is calibrated, I can actually measure with quite high accuracy how far away that is. On the other hand, points that are in here, looking at any of the white pixels on this floor would not be a good feature point. Right? It'd be very difficult to track white points on the white floor. Edges are better, but they only allow us to track points with respect to one direction. Like if we didn't have if I use the walls there, right? Where the wall meets the floor.
Okay. Oh yeah.
If I use those lines, or when we were playing with our soccer playing robots, then the field lines, because the field of view of the robot is not so big, so you see some field lines, you can use those in order to estimate your motion, but only within one direction. So if I move away from that line, then I can measure that. But if this is my field of view and I don't have the grids on the floor, then I don't actually, I get the same image independently of how far I move along the line. So we cannot measure movement along the line, but off the line, like closer into the line or further away, or rotations, relative orientation towards the line, we can measure quite nicely. And that's actually enough in the soccer domain. We implemented quite good localization algorithms just using the field lines. If you can detect those well enough, then you can track your position. But that's also okay in the soccer domain, right? Because there we were mostly interested in the sidelines, because the sidelines tell you the direction and how far away you are. So then, what does the soccer playing robot do? We sort of pick up the ball if we can get it, and we start walking towards the opponent's goal. That information I can get from the sideline alone. Whether I'm actually at 1 meter, or whether I'm actually 3 meters away or 4 meters away from the opponent goal, given the current state of robot soccer, that's not terribly important information, because the robot is going to do exactly the same thing, right? It's simply going to keep walking. Eventually, you're going to see the other goal. And once you see the other goal, then you start kicking. So if you're, the sidelines worked really well in that sense, that they provided us with all the information that we needed. And the rest, the algorithm would sort of naturally just do the right thing. But in general, corner points are better, right? Because they allow us to detect motion in any direction. Now, one other interesting thing about optical flow is that the algorithm that I described is going to be, you're considering, or you may consider it to be a fairly simplistic algorithm, but optical flow is a nice problem because it actually, there's sort of a tendency in artificial intelligence research that we design ever more complex algorithms, right? Most of the real breakthroughs in AI, like let's say deep learning, for example, case-based learning, which I liked, which was a big change in planning, in the way that we approach planning problems. That was the initial idea. The guy that invented it implemented it, and it gets like 80% of the performance of that particular technology. And then there's another 30 years of research to push it up from 80% to 92%. The way that is usually done is by adding more and more knowledge into the system. So deep learning, for example, you then add more complex loss functions to sort of feed back some more information into the system. The more information the system has, the better it can work. Or we cover edge cases, for example, things like that. But at the same time, adding this extra information needs to be processed. So usually the algorithms sort of slow down. But optical flow is a pretty nice problem, because as you, it crucially depends on your processing speed, right? As your algorithm becomes more complex, and people have tried to design more complex optical flow algorithms, as your algorithm becomes more complex and it slows down, it actually becomes a much harder problem, because if you can track, if you have an optical flow algorithm that runs at 1,000 frames per second, right? It's very, very fast, very simple. The one that we described can nowadays on a workstation runs easily in at 60 frames per second. Right? You can run it at 1,000 frames per second. If you need to track points at 1,000 frames per second, it's actually a much simpler problem, because every time you get a frame, the pixel can have moved maximally by 1 pixel, unless you're moving very, very fast through the world, right? But so your search space is kind of like 9 pixels, right? That the point may have moved to.
When we're low. You're saying when we're low. When the movement is low.
When the speed of processing is fast compared to the speed of movement. If you're running 1,000 frames per second for a robot or a car that drives through the world, right, that's going to be very, very fast. That means 1 millisecond you get an update. Every 1 millisecond just need to, actually, it in a sense, you only get 60 frames from the camera. So anything above 60 doesn't really matter, right? But let's say you could. 1,000 frames per second, optical flow is not a big problem, because your search space is area of 9 pixels. Right? That's a maximum that the thing could have moved to in such short time. If you're a cruise missile, then of course, yeah, it would move faster and may move more, but usually no. Now, if you have a more complex algorithm, and now you only run at 10 frames per second, then all of a sudden you need to consider many, many more combinations, right? Your point now will have moved to a 16 by 16 area, which means that then there's a much higher chance that there's interference, like one feature moves into there and you may misattribute it with the data association may be wrong. All of those problems don't occur if your algorithm is lean and simple and fast enough. So for optical flow, often a simpler algorithm with a higher frame rate works much better, because the problem that it's trying to, that it has to solve really is much simpler. Now, for the optical flow algorithm, we use the Lucas-Canade algorithm. It uses a specific set of feature points, Xi Tomasi, which are calculated. Last time we did the slides with the feature points. We talked about the Taylor expansion of the moving the pattern across, and that's basically implementation of that. So we minimize the square difference between neighborhood of pixels in the previous frame and the new frame, and we want to get the X and Y offsets that minimize those differences. So we have a patch in the image, and we basically look for another patch where if I shift those two, then the error, the mean squared error, the least squared error is going to be minimized. And then there's a version of an extension of the Lucas-Canade algorithm, which weighs pixels in the center of the neighborhood more highly than pixels at the edge. And that's because when we run the algorithm like that, then pixels on the edge often drop out of the frame, right? So they disappear, or there's more noise in them, and because they are sort of at a bigger angle, and then that means they're not such good points to actually try and track. Then, because when you're tracking a point, it disappears, and the algorithm is trying to find that area though somewhere, so there's a high chance that it will give you a wrong result, a wrong classification, a wrong motion vector. So we can look at the implementation of the Lucas-Canale algorithm, and that's what I have here for particular for that particular video. So first we set up the parameters, the maximum number of corners we want to track. Now usually this would be a lot more. I just wanted to run fast on the callout, so I set this number very low here. The minimum quality, the distance between feature points, and the block size, which is the so it's a 7x7 patch that we're trying to match using least squared error. For the Lucas-Canale, a number of parameters. The most important one will be the win size, the size of the window that we allow to track, where that point will have moved to. And here, like most computer vision algorithms, we want to work in the grayscale image. And here calculate the feature points, and then we can here I take out the neighborhood of one of the points just to show it, and then see what kind of picture. Like here, this one, we just want to get a feeling for what kind of feature points the algorithm actually tracks. So here's one of the feature points that we track. Be the 7x7 there. Okay. Now they have must be features. Hold on, I want to resize it just to make it a bit faster. Yeah. Here will be our output video for the first couple of frames, and you can see the points that we're tracking. But now I want to run the same thing again. But I want to 8 seconds, and I want to resize the frame. And I think that should be all. So now also the things are easier to see. So you can see the feature points that it found. They all seem to be on corners, right? They seem to be reasonable feature points. And now they keep moving around. Now, if you paid attention, how good is the result, or is it good or bad? Any obvious errors that we saw?
So it basically moves how the camera is moving. So the lines are drawn based on how the camera is moving.
Correct, yes. So that's the trajectory of that green point throughout the entire video. I just keep adding to draw the full line, but you can see, like here at the beginning, here we start. So that point was originally there, now I move to the left. Now the camera is panning to the left, so the point is moving to the right, if you track that green point. So we can look at the green point. And it actually, it didn't want to start. The green point there is tracked very nicely. There's no errors.
And once the green point is like out of the frame, it will stop.
Yes, of course. So that's one problem, right? Once the point is out of the frame, then there's nothing I can track anymore.
Oh.
So then that point kind of becomes useless to me. Now, that's one thing you would need to do in practice. I think. So here, you can see how I take the status of the points, and I check the ones that have a status of 1. And that's then the good new points and the good old points that I have. And the ones that have status of 0, those are the ones that dropped out of the frame.
We set the status of 1 initially.
No, the algorithm does it. You cannot find it. So basically, the way that the algorithm works is we have I think 7 by 7 area, and we have a 15 by 15 window, and then I calculate this, and I try and figure out which way did this 7 by 7 patch move, and minimize the least squared error between those two patches. So I'm tracking these feature points, which usually are some kind of patches.
And the 7 by 7, that's initially detected.
That's initially detected in the first frame as good points to track.
And then it uses that as basis
for
the next frame.
Correct, yes. For what to look for next. Now, if we can find that, and I set the quality criteria, and I think I set it to 0.3. If it can find it, then it'll return that. Otherwise, it's going to return some point with a status of 0, basically says that I can't find any place where that would be a good match, and still satisfies the quality criteria. In that case, then it gives up, and that point gets a status of 0. And that's usually what happens if the point moves out of the frame. Right? There may be other reasons why that happens. For example, if it's a dynamic scene and there's occlusion, somebody walks in front of your feature point, then you won't be able to track it anymore either. But the set of points is what we track here with our optical flow. Now this is using the image pyramid version of Lucas Canade, but I think I set the level to 1. Yeah. So the image pyramid is this kind of idea. If I want to check changes in scaling of the image, right? Then there's really no efficient way of doing that computationally. The best thing, or one of the approaches that we can do, is we can take the image and simply pre-scale it to different sizes. In the image pyramid, you take the image and you apply Gaussian blurs and then compress it. And the hope is that then the same feature point will be tracked through the different levels of scales. That's the SIFT feature idea, and the Lucas and Canade idea. The surf feature points, they used a slightly different approach. One way is to have one filter, like here we have the same 7x7 patch that we're looking for, right? And here I look for 7x7 patch, and here I look for 7x7 patch, right? So in order to be robust to changes in scale, I can take the image and compress the image, right? The surf feature does it slightly differently, computationally more efficiently, they claim, and I think it's probably true. They start by using different feature detectors. So initially they have a 7x7, right? And then we try 15x15, and then we try larger and larger features. So we blow up the size of our detector, but all on the same original image. So we basically just figure out and change that. And that, of course, is basically trying to do the same thing. And there's different, it's not just by a factor of 2 always, right? That would shrink it down too fast, but you can scale it down by certain kind of percentages. That's what they would call the octaves image pyramid. But in this particular scene here, I'm not so worried about changes in scale because most of the points are pretty far away, so even changes in scale are not going to cause a big problem. So I set this, I think, is the maximum level of the pyramid, so I only work on one level in this case. And here, when I calculate the optical flow, using Lucas and Canale, then you can see I use initial points at P0 here. Those are the points that I want the algorithm to track. And those are set from the good new ones. So if a point drops out, I don't keep trying to track it. And as you can see, the algorithm does a good job with this particular video here, if we look at it. But now pay attention. And there, that was a huge mistake.
Oh yeah, that one.
The one we didn't just move straight down, so the point moved way up there. So here we actually switched from this location to that location. It simply misfired. Right? It found the wrong correspondence within the window that it's trying to look for. Now we could. How can we fix that? Well, for one thing, I think I can change the size of, let's see what happens if we change the size of our window here. 9 by 9 instead of 15 by 15.
So the window is the video size.
The window would be this size here.
Oh, okay.
The area that I keep looking for that dimension.
Right. And the little squares there, that's the patch then.
That would be the patch, yes. So that's, I define that in the good features to track call. So I set that to 7.
Right.
I think that's what that does. Oh, wait a minute.
So essentially,
No. Not quite. Right. No. It's not quite like that. No, this is the original, first cut only for the good features to track. So these are the first points that I find. And then we use this patch to track. And that's only 11 items. So that doesn't do this. So that won't, that now just looked for the patch size that we're trying to follow. So there's only one parameter anymore. Lucas Canada tries to look for that area. So here, if we have a mismatch, then now we should have more of them. Possibly. Yeah, so now we got an extra one here. I thought there was a parameter to limit the search area for the Lucas Canada, but I don't think it actually does. I thought we specifically passed it. Yeah, so there's more there.
oh wow. Basically, what it tries to do is like, so the patch will move on what it thinks to be like the original patch when we're trying to move the camera.
No, it takes the neighborhood of those pixels from the previous frame.
One. So I'm guessing the reason why there's like a sudden drop.
Mm-hmm.
So it thinks that the patch before when moved to a different frame, there's something similar to that.
Yeah, it just happens to be something that's in the image that is all of a sudden, like here, this moved from there to there, but
Supposed to
now
be
it's a
here.
little bit in the shadow.
So it thought went down.
So
to
it
the
thought, oh, this point actually matches this area much better. So it went, instead of going here, it went to there.
and there. Oh. Would it change things? Oh wait, but you already changed it to gray.
Yeah, it's grayscale.
Is it a shadow? You already made it into gray. I thought it's.
Say again?
Yeah, because I was thinking if like maybe the video was originally inputted as RGB, and we already converted it to gray.
Yeah, and the processing is all done in grayscale. Which may sound crazy, but it actually is the right thing.
Yeah, it is the right thing.
Colors are so variable that you can spend a lot of time tuning colors.
Right.
So you can see now, by increasing the neighborhood, I now made the pixels more unique. Right? The patches that I followed are now more unique. So now we don't have any error in there. I'm not sure about that green one here. These are actually correct. I don't think that was an error. So I think that movement is all very nice.
Yeah.
Right? So now we tracked everything correctly. So that's a Lucas Canade optical flow algorithm. Now, there's a couple of problems with it at the moment for our application. I already deal with the problem with points dropping out of the frame. Right? They will simply not be used for tracking anymore. Right? So that the new points are only the ones that are actually tracked. Now, there are sort of two ways to think about time in optical flow computations.
Question. So if the points that it initially got from the initial frame were suddenly out of the frame already, it already stops tracking. So it doesn't like pause the tracking already. So one like if this is one point, it goes out of the frame. Then what if the camera goes back to it? It doesn't.
Usually, it doesn't recover from that.
So it doesn't recover it anymore.
You could do that,
yeah.
Right? And in fact, one of the things that I wanted to bring up here is sort of the two views of time. So we already take care and by using only points that were actually tracked. So points that moved out of frame, we don't track anymore. But for a more robust implementation, you can back project the points that you found, and you basically then only pick points that from the current frame you can find where the new one, where you think the new frame is, right? But you can then also go back and project it and say, oh, that point, I've actually been able to track that for the last n frames, so I'm pretty sure that's the correct point, right? You can also then do sort of sanity analysis or sanity checks, right? If it's a moving robot and that point just moved 100 kilometers per hour, hundreds of pixels, if it just jumped for hundreds of pixels, then probably something is wrong in the tracking. So you may decide to throw that point away. Your optical flow algorithm may decide to throw that point away. You can do that by back projecting it, because you cannot look into the future, but you can certainly look backwards. And you can also keep track, a cache of points, and then go back to a point that you have seen previously. But that, I think, is only certain domains where this would be really useful. That would only be useful if you really have very strong, globally unique points in your environment that would help you in localization more than actually optical flow calculation. Now, what's the other problem with the Lucas Canale tracker in this case? For the points that it tracks, it does a great job, right? There's nothing to complain about there. Usually we don't get it so nice. But if I look at that image, the bottom of the image, I have no information about the movement at all. I don't know if this is consistent with the motion that I estimated or not. Because there's no points below 300. Right? Or with a y coordinate of higher than 300, I have 0 points. So I have no information about that, really. So that is a pretty common problem. So, and that's something you want to took a lot more points. When I make bigger motion, so then you get more error in the image. Here I just sample every 10th frame instead of every frame. And that's just to show what happens as if that's the same effect as if now the person would have been moving or the robot would have been moving faster through the environment. But let me try one thing and let's see how that works. So how can we fix that problem with selecting more points in the bottom of the frame?
Increase the line on the bottom.
Pardon?
Increase the brightness of the bottom. I don't know.
No.
Because I'm guessing that's the reason why.
What's the actual reason why that happens? We can't really tell. We can't really tell it, but it depends on the tracking of the algorithm, right? And the good features to track, it will give us the 100 best points. And our feature tracker, a lot of it depends on difference between the patch and if I move it around, sort of the corner feature, right? The abstract corner feature. And of course, if you have brights there, then there's going to be a much bigger change than in the dark area here. So it will be, it's not possible to get 100 points. If you want the 100 points that have the strongest response to shift, they're all going to be in areas of very high contrast, which you can only get if you have brightness.
Right.
So if you want to do that correctly, or if you want to have points in this region here, then you have to tell, basically you have to split the algorithm into two components. One, and tell it to give you, if you want 100 points, you want to ask for 50 points at the top and 50 points in the bottom of the image.
Oh.
And then combine them. And of course, Slam, which is basically the same idea, except instead of using good features to track, we use the orb feature points. We could have done the same thing, it wouldn't have made any difference. It does that, it breaks it down and makes sure that the density of the points is sort of uniform across the image, or uniform across the center of the image here, right? Points at the edge are usually not good points to keep tracking because they are the ones that are likely to disappear. But the center of the image is sort of the center of motion of your optical axis, not necessarily, basically your horizon line is where that comes into play. So let's try that. So modify the code so that we track now different sets of points for the top and the bottom of the image. No latency. Anyway, that's not so difficult to do, right? Because the main argument that allows us to control that is our points here. So basically, I just need to break the image down. In this case, the top and the bottom part, right? And then I need to track the pixels through the entire frame. So one thing that is missing there is P0B, the y coordinates are going to be all wrong because they're all going to be 320 too small in the original frame if I do that. Because here I take the bottom part and that has y coordinate 320, but then when I pass it in there, it has y coordinate 0. So I need to go through P0B and add 320 to every y coordinate, but I'm not sure exactly where that is stored in the P0B. So that's why I wanted to actually print it out first. Unfortunately, the Google thing crashed, so the collaboratory crashed, so I have to restart the entire notebook. But that's okay, then that will work. Also, this implementation here is the way it works right now is I have a set of points, right, from good features to track. Then I use the Lucas Canade filter to actually track them. If one of them drops out, if I cannot find a good match for one, I drop it out. Either the point moved out of frame or I just can't find it anymore. Maybe occluded from my new point of view. Like if I use the door handle, right? In this scene, even though nothing moves, right? It's a static scene, and I look at the door handle, then I can see the door handle, very nice, can track it very nicely. If the robot goes down, now I look at the monitor, so I can't see it anymore. So due to occlusion, we may also lose points. At the moment, the algorithm does only lose points. It never gets new points, right? Which means if I run this long enough, then all the points have disappeared. The algorithm will have nothing to track anymore. So that's why you also need to have a step, usually in the algorithm, where we select a new set of feature points. Now, those feature points, you want to keep the old ones, because the old ones give you some very strong indication. If they're all moving in straight lines, their dy, dx all matches to the movement of the robot, then they're very good points to track, right? You've been very successful tracking them through the last n frames, so you don't want to throw them away and just start with a completely new set of feature points. On the other hand, you do lose points, so eventually you want to add new points to it. So different approaches exist. I think what I did is, I think I had like 25% of the points were new points detected by good features to track, and 75% of the points were the old points. So I took the 75% best matches from Lucas and Canade, and I replaced it with, I added 25% of new points in every frame. And then that gives you a reasonable good spread of points as they go through the image. For our scooter visual odometry algorithm. Let me see if I can get that back in shape here. So sometimes this is also quite interesting to look at the feature points that you actually found. To make, like, print, if you actually, implement this on a real system, you want to print out a sample of the feature points that your algorithm actually is tracking to make sure that you think those are reasonable points to track. And yeah. Now here I want to try. How come it comes even to math? It should quit. Okay. 128, 84. Oh, yes. Okay. And this would be y-x coordinate. Okay, so that's actually easier. The status only comes from Lucas Canale, not from the feature tracker. So here that would be y plus 320 plus 220x for yx okay, then it seems to stack them. And then let's see what video we get. Is tracking resize thing. it's a list of lists. This is just to get the lists in the right format so that our trackers like it. We need to change that. P0A, P0. P0A, P0B. To P0A. So P0B. And then P0. think that's it. Float 32, float 64. Oh, because I hadn't changed the key again. But yes, so the problem was the Lucas-Canada algorithm requires float 32 arguments, and we gave it, we got a float 64 or something. Yeah, no, we got it. Hmm. Now my session crashed. Okay, let's give it one more try. And of course, I don't really want to use it as two separate images, right? That's why I want to keep it in frame, one frame buffer, because a point may move from the bottom to the top, and I still want to be able to track it. So it's not the same as running different Lucas Canade trackers over two separate images. There's some overlap. See, I don't really use that much resources. It's only green. Okay. Now let's see what happens. Hmm. I'm not really getting points in the bottom. So here my quality level is too high. I think I can override it like that. So the number of points is just the maximum number of points it may return. If it can find them with the correct quality level, then it will generate fewer points. I think it will generate. So any kind of optical flow based on features, the selection of the feature point, the distribution is quite important, but that depends a lot on what your application is too. Some strategies work well in some domains, but not in other ones. Something like wrong doesn't. Because yeah, here we actually have much fewer than 100 points. So there's very few points that meet those criteria. So we can set that lower. Okay, now we have more. A lot more. So by the way, how do we deal with the error? Like whatever I did before, you saw the point jump like this, right? If I now try and map the motion of the camera to the way that the points move, then that's going to give me an error. So what do we actually, how do we actually extract the motion of the robot given the tracks of the points?
Extract the motion, you mean
The motion of the camera.
Those lines right there.
That's how the points are moving, right? But I want to know whether the robot moved forward or turned left or turned right. Now, if the robot turns left, right, the points are going to move to the right.
Yeah, to the right.
But then, how do I calculate the degree that the robot turned?
We need to include the pixel coordinate.
Yeah, we have the pixel coordinate. Yeah.
From the features and compare the calculated trajectory.
Yeah, yeah.
Find the.
But the point is, there's no the trajectory, right? Because every point has a different trajectory.
Yeah. But they should all be going in the same direction, right?
If we turn, yes, they should all, actually they should all be turning by the same number of pixels, right?
So that can be one method, no?
But, so first thing, of course, is the pixel coordinates. There's some noise to it, right? And what we can do is we can calculate a regression, right? The least squared error of the movement over the sum of the points, right? So then, in order to detect the motion, we kind of have, it's similar to trying to detect the position of the line, and then we're trying to calculate the least squared error line approximation.
Right. More sophisticated, yes. A bit more sophisticated than my idea of, okay, let's get the direction.
Yeah. But the big problem with that is that we can pick any kind of algorithm for doing that, right? But if we lose a point, then we get a point here all of a sudden, right? And then what happens if we calculate, if we use least squared error as our optimization criteria, what will happen to our line?
Negative slope.
Negative slope.
If you lose 1 point.
No, if this point is added here, right?
Oh, then it goes lower.
The problem is that this point is an outlier, it's an error, right? But because we use the least squared error approximation, as our error increases, we square the error, so it has a much bigger influence. Which means that even though I may have a lot of points here, the line that we estimate all of a sudden will be this line, right? So a single point that is wrong will have a huge impact on the final output. And since because of occlusion, because of points dropping out, because of things moving in the scene, those are all very real, very common problems that we're dealing with in this scenario. That means we cannot really apply the kind of least squared error approximation that you're used to from fitting lines, fitting polygons, any linear regression algorithm. It won't work very well. It'll work horribly bad. Because a single error point, right, is going to completely throw off. In fact, the only thing you know with this line here is that none of the points support it, right? It's far away from this point, it's also far away from any of the other points. So it's the most useless line we could draw. So any ideas how we can deal with that problem?
Wait, so we're using a line?
No, not really a line. We're trying to map a line into the
to try and find the angle of rotation.
Angle rotation and linear movement. That will be the first step, which would be our visual odometry part. So I want to move from between frame n and n minus 1. How far did I move and in which direction did I move? I only did the line because you're probably familiar with it from high school, but it's the similar kind of problem, right? Instead of mapping a one-dimensional, two-dimensional feature like a line, I sort of have a three-dimensional feature where I need to map line and rotation. But the problem is not so much with what we're trying to regress, right? The problem is how do we deal with the outliers?
Can we just ignore them? Because we know.
Sure. I give you 1,000 points, and if you can ignore the outliers, then that's okay, right? That's what we want to do. We want to get rid of the outliers. But how do you know which point is an outlier and which point is not an outlier?
Example, 25% of the most outer, like the values, the extreme values. No?
But if you only keep the middle 75.
Right. Yeah. But the problem is, with that, I don't know what the middle 75 are. The idea is good, right? But I don't really know which one the middle 75 are, because they're like these points, right? But this may be 0.1 or 0.1000. I have just, so basic, but the idea is correct. What we want to do is calculate a model, in this case a line, given some of the points, right? And then we want to check how well does that model fit the other points that I have in my system, in my data set, right? And if all the points fit and they're reasonably close, then I think I found a good model. If there's a couple of outliers, I can say, okay, those are probably outliers. If only 2 points map, if I do this in this particular scenario here, and let's say I take these 3 points, 1, 2, 3, and then I map a line through it, then maybe I get this line, right? If I get this line, then I can check these other points, they all match as well. They're pretty close to the line, so I think this is probably a pretty good match because most of the point match are within sort of a boundary error that I accept for this line, and I think that's possible that that's due to noise. And then here I have one outlier. Okay, well, there's one outlier then. Right? If I pick those 2 points, if I pick those 3 points, 1, 2, 3, then I'm going to get a different line. But that line is going to be supported by much fewer points. Right? And that's kind of intuitive, that makes sense, right? And that's actually a pretty clever idea too, and it's called the, do you know what the algorithm is called? It's called the ransack algorithm. You haven't heard of this before? No. Random sampling and consensus algorithm. And it basically just means exactly that. Then there's quite a bit of research literature. It's a well developed algorithm. It's what you have to run every time your data set actually has some outliers. If you want to apply least squared error approximation, which has many benefits, can be computed very efficiently, is numerically stable, has some very nice properties, but gets completely thrown off with outliers. Then, if you do have outliers, you need to apply this kind of ransack algorithm first. And we basically do exactly what I described here, but we'll talk more about it next class. So next class will be about the ransack algorithm in order to be able to come up with a motion estimate. And it's a pretty neat algorithm. The most important thing to keep in mind is that for the approximation for the regression step here, we use the least squared error, right? To measure the quality of our model. For the ransack algorithm, we don't use the least squared error. Because if I do that, I end up with exactly the same problem. But we use the consensus. How many points are actually close to that model that I just calculated? So it's a number of points that this model is close to as opposed to the least squared error approximation.
I got lost for a second. So these points are the features we are extracting, right?
In this case, it will be the features that we extracted. Yes. You can say I tracked. Actually, it could be one feature, a single point that we tracked over 100 frames.
Right.
Then I would get a line, right? Then I want to track what line, how that actually moves.
So this is to solve the feature matching? No.
To find
to find the actual movement of the camera.
Right. The poses.
Angle rotation.
Okay.
How we move.
Yeah.
And
to get a stable estimate of that.
Okay. And the result of ransack could be any model as long as it finds like the best model that fits the feature.
Correct, but best is different defined from linear regression. It is not based on the least squared error. It's based on the number of points that are within what I would call like a noise band around the model. Like if we look at the video here, right? Then okay, definitely 1 pixel shift is not an outlier, right? That happens quite often. And probably 3 or 5 pixel shift is also not an outlier. 50 pixel shift, definitely an outlier.
Would things have changed if we applied like noise filter from the beginning instead of?
But I don't know. It wouldn't change dramatically because what kind of noise filtering could we do? I mean, the points are moving, right? It's not stationary, so I can calculate the average, exponential average over the position. We could filter and smooth some of the points moving here, but that is not what you want to do if you do have to worry about mismatches. If this point jumps from here to there, I don't want to filter that because then I get some phantom point somewhere in the middle there. Right? So in this case, if there is an outlier, I really want to throw it away. And there's no way to avoid that problem in optical flow. There's many scenarios where you will get a misalignment of your like in the first video that I had, I didn't get any, but that's because it's a very short sequence and I just got lucky with the parameters.
So by next week, let's say we try to apply the optical flow to the orb feature extractor. So we use the orb to the orb.
Up to you. I think they will both work perfectly fine.
Oh, okay.
So for the, you mean for the German project?
No, yeah, just to practice.
Yeah, you can just implement that and play around with the parameters. Right now here, I just actually got a couple of more points there, but I didn't get any. I didn't get any points in the floor. There's just not enough in the grayscale image here to get any kind of feature points. So at some point, if your robot is looking at a white wall, you just have to accept the fact that you won't be able to do visual slapping. Then you just have to use other. Oh, there was a point there. But we did get a bit slightly better distribution over the. So I like the algorithm a lot. I think, and it's actually quite simple. There's no. No complex mathematics involved. So what kind of math did you say you were actually doing?
That yep. I applied mathematics.
Okay.
So all maths.
Yeah. But no projective geometric
we did
algebra.
We did that.
EGA. Clifford algebra and everything. Okay. So what do the mathematicians think about
that? There's kind of divided. One end, why would you do that? Why would you do that?
Yeah, I'm at the same.
If we have multivariate analysis already, which is like 3D calculus, like why do you have to do that? You have this already. The other end, it's more useful if you have it like.
Okay, it's a tool. You should know about it. Okay.
Yeah.
I just think. I mean, it's interesting right now. if you have done any 3D programming or kinematics of robots, computer graphics, then the engine that was driving the whole thing were the homogeneous coordinates and homogeneous transformation matrices. So you have a 4x4 matrix and you can model anything that you want, right? But now, for rigid bodies, you can actually use these Clifford algebras, which can then be specialized to quaternions and lines and planes and everything. And that's kind of cool. And the problem with the matrices is, I do agree that, I mean, there's a lot of redundancy in the rotation vectors, and interpolating between the matrices is not easy at all. So now actually there's a big change in robotics, kinematics. A lot of people now trying to reformulate inverse kinematics to use PGA and then you have your exponent and log methods. Yes. And also SLAM is now completely sort of changing away from 4x4 transformation matrices to use PGA. And for SLAM, it makes a lot of sense, right? Because you are then guaranteed to get a motion that the robot could only do. But practically, I guess I will be, if you think back about artificial intelligence, and there were sort of the idea of the needs that wanted to have a formal theoretical foundation for intelligence, and the graphies we just wanted to get stuff to work. And so I'm definitely in the later camp, I think. But I do think we need to change our inverse kinematics. I think that's actually a pretty good idea, and particularly for SLAM, where on the other hand, I kind of like the 4x4 matrix, because there is a bit of redundancy in the representation, right? So, but my view was always that if there's some noise in the data, then when you optimize and you calibrate your camera, for example, or you calibrate the motion of your robot using visual SLAM, then you didn't get the nice orthonormal rotation matrix. But I always saw that as sort of an additional feature, because the algorithm had a couple of extra parameters that it could cheat, and it still matched the points really well. If you force it to have just one rotation angle instead of like 3 values that it can play with, I'm not sure if in practice that will actually give you, theoretically it should give you the correct result, of course, but that's if your data is clean. It's not so clear to me if you have noise in the data. I always thought these matrices sort of had some built-in error buffer, just because there is some redundancy in the representation, then you could, the order in which you can calculate things will give you a special result. So the algorithm sort of knew that, and I never minded that. But right now there's a big change in robotics using skew matrices for camera calibration and visual odometry, and also in computer graphics now. Except computer graphics is slightly different, because the PGA-based approach only deals with rigid body transformations, so it doesn't really do scaling. But of course, in computer graphics, you want to zoom in like in some camera shot, right? And then that is not so easy to model.
Can I ask a stupid question? But when it comes to camera calibration,
since we have very limited cameras, isn't there anything like an online database with the calibration files for cameras?
There may be, but it's usually not. It's usually not necessary. Like I wrote there's two parts to the camera calibration, right? Either the one part is the intrinsic parameters of the camera, and the extrinsics, which is the position and angle and pulse of the camera with respect to the scene. Now, the intrinsic parameters you could get off a data sheet. I'm sure if you search the data sheet for the sensor that is built into the Logitech CM920, then somewhere there is a data sheet that tells you exactly what that CMOS sensor does. But practically it's not useful per se, because you can just you get a good enough approximation just having a calibration tab. So
I'm trying with the checkerboard, I'm wasting a lot of time. I mean, I think I just need to find something to go.
So I wrote the thing so that I can just use the phone. I hold it up in front of the thing. And actually it's the web server runs on the robot. So I connect to the robot, it sends me the picture, and then when it can actually see, it can vary the sizes of these things so that it gets a good match, and then you just have to wave it around a couple of times. It saves its calibration. I think the intrinsic parameters then are good enough for all practical purposes, and I think that's probably more practical than trying to find the right data sheet. Because the intrinsic parameters also should never change, right? Once you have to calibrate. And the algorithm does a pretty good job. The extrinsic parameters you need to calibrate quite often. But then if you do have the intrinsic ones, then you only need 6 points to be able to calibrate the image.
Thank you.
So why are you interested in camera calibration? Then I can cover camera calibration in the course.
Because I'm working with Islam a bit with my thesis. So I'm trying to use all Islam 3 and just.
So then you know all of this already?
No, absolutely not. That's the problem. Because I'm trying to study it on my own, but it's tough. I mean, it's complex. It's not really. It's not really. If you're not from the field, like if you don't have a very strong engineering background, like I come from computer science. Sometimes the papers are like, as you mentioned.
But that's because they write it in a mathematical notation.
Exactly.
If they were to give you the Python code like me, then I think it would make a lot more sense. I would hope at least.
So that's why I now managed to install it, and just installing it all the libraries and everything was a lot of time. And now to run it, actually, I need to calibrate my device. And I discovered that calibrating the camera is not as easy as I thought. I thought it was just like, okay, sure, but actually it's a lot of work. That's why I asked if there is any kind of preset.
No.
There isn't. All right.
And even if you get them from the data sheet, I mean the pattern shouldn't be a big problem, right? You have a problem with the.
No, I created it, but basically the software acts on some kind of open source solution to calibrate the camera.
The OpenCV has it built in.
I'll try with OpenCV then. Okay,
OpenCV has the John's camera calibration method built in. So that's what everybody uses.
Oh, right. All right. See that. Maybe. Okay, I know.
Yeah.
Thanks. All right.
And that gives you the cubic polynomial approximation for the lens distortion. Actually, if you may not even need to calibrate it unless it's a wide angle length. There's not that much distortion on the.
I need, because I need to convert into something like backwards, like Orbislam has a very specific
file format to work with. I can't feed my video into directly like MP4 file, doesn't work like that.
Oh, but that has nothing to do with the camera calibration.
I need the camera calibration for generating the. I think it's necessary. I'll look into it.
Yeah.
Look into it anyway.
Okay. Yeah, good.
Thank you very much. See you next week.
Okay.